Now let us see about von Karman momentum integral equation. In the introduction of boundary layer theory, we have seen that this boundary layer theory should be studied so that we can find what is the drag force and how does it affect the vehicles, and we can design based on that drag forces, we can design the vehicle. So now, in order to find this drag force, we can find the shear stress. From the shear stress, we can find the drag force. So what is this shear stress? This is given by von Karman momentum integral equation. Assumptions of this equation is the flow should be steady, and it is a 2D flow, and it is incompressible flow. So these are the assumptions of von Karman momentum integral equation. So von Karman momentum integral equation is given by tau naught x is equal to tau naught x divided by rho u infinity square is equal to dou theta by dou x. So what is this tau naught x? So tau naught is wall shear stress. If you observe this plate, from here it is x. So here there is a wall shear stress, here there is different wall shear stress, here there is another wall shear stress, here there is another, here there is another, here there is another one. So that depends on the wall shear stress, depends on x. For example, if you consider at this point, the small thin layer will give us wall shear stress at that point, at that position of x. Now this is the von Karman momentum integral equation. Then what is this drag force? First, this shear stress is also given by Cfx by 2 into rho u infinity square. So what is the Cfx? Suppose that if you are on the ground and there is air blowing in this direction, if you are trying to move in this direction, there will be some resistance and you need to apply some force in that direction to move forward. If you are if you are in water and the flow is in this direction and you are trying to move in this direction, so in which case you need to apply more force, in this case or this case? So you need to apply more effort in this case. This is because it is of the water is of high density, and also it depends on the velocities and all. So it is a material property. So this Cfx is dependent on some material property, density. Now, so how can we find this drag force now? We will find the Cfx in the later case. So now first let us find drag force. We have seen that if this is the plate, so this is the plate and this is width b. Now if I consider this is the x direction, so I am considering it at x direction, at a distance of x. I am considering this small strip of a length dx. At this point of x there is shear stress tau naught x. So the drag force will be this is x is equal to 0. Here x is equal to L. Length of the plate is L. Integral 0 to L. So what is force? Force is equal to shear stress into area. So the shear stress into area. What is the differential area? Dx into B. So dx into B. This is the force. Now what do we need to find? So B comes outside. Integral 0 to L. Tau naught x is Cfx by 2 into rho u infinity square dx. So now rho u infinity square into B comes outside, by 2 also comes outside. Integral 0 to L Cfx dx. So this is what drag force is. Now drag force can also be represented as CD by 2 into rho u infinity square into area. Area means area of the plate, that is B into L. So this is the drag force. This is called as average drag coefficient, and this is called as skin coefficient, skin drag coefficient. So skin drag coefficient means at a particular point of x there is difference Cfx, and for a total plate there is average drag coefficient, that is CD. Now equating these two, so this will be CD by 2 into rho u infinity square into BL. Now rho u infinity square B 2 gets cancelled, and CD will be 1 by L integral 0 to L Cfx dx. So this is the relation between CD and Cfx, average drag coefficient and skin drag coefficient. So that is the relation between them. Now how to find these values? Let us see now. For example, the most important velocity profile is given by u by u infinity is equal to 3y by 2 delta minus y cube by 2 delta. So this is the most important velocity profile. Now applying the von Karmann momentum integral equation, rho tau naught by rho u infinity square, this is tau naught x, is equal to dou theta by dou x. So we can write this d theta by dx, as this changes only in x direction. I am writing it as d theta by dx. Now we know that theta is equal to 0 to delta integral 0 to delta u by u infinity into 1 minus u by u infinity dy. So we know this momentum thickness. Now substituting this u by u infinity in this u by u infinity and u by u infinity, I am not deriving this totally, and it is also not important, so I am not deriving it. Then theta is equal to 39 divided by 280 delta. So you will get theta is equal to 39 by 280 delta if you substitute this u by u infinity in this equation. So you got theta is equal to 39 by 280 delta. If you substitute this theta in this, we will get tau naught x is equal to rho u infinity square into what is this, d by dx of 39 by 280 delta. So what do you get? Rho u infinity square 39 rho u infinity square divided by 280 d delta by dx. So this is tau naught x. So you got this. And also for laminar flow, if it is a laminar flow, we know that tau naught is equal to mu into du by dy at y is equal to 0. So we know this. If you substitute this, u is equal to 3y by 2 delta minus y cube by 2 delta sorry, this is not a delta, this is delta cube. So if you substitute these values, into u infinity, from where did I get this? This one. Now if you substitute this in this, tau naught is equal to mu into du by dy. Differentiating with this with respect to y, we get 3 by 2 delta, differentiation of y is 1, minus 3y square by 3y square by 2 delta cube into u infinity, where at y is equal to 0. So y is equal to 0 means this will become 0. So 3 mu by 2 delta into u infinity. This is tau. Now we got this one and this one. Equating this both, 39 rho u infinity square by 280 d delta by dx is equal to 3 mu by 2 delta into u infinity. This u infinity, 1 u infinity gets cancelled, and taking this delta to left hand side, delta d delta is equal to 3 mu by 2 into 39 rho u infinity into 280 dx. Now solving this will be delta square by 2, integration, doing integration, that will be delta square by 2 is equal to 140 13. So 140 mu by 13 rho u infinity, and these are all constants. Integral of dx is x. Now from this, delta is equal to, if you solve this, we will be getting delta is equal to 4.64 under root of x into mu by rho into u infinity. This can be written as 4.64 into x by Reynolds number at x. So just remember this formula. Delta is equal to 4.64 x by Reynolds number. Reynolds number is rho u infinity into x by mu. Rearranging this, you can simplify that. We will be getting this one. Delta is equal to 4.64 into x by Reynolds number at x distance. So you have got delta. So from this, there is an important relation. Delta is directly proportional to root x. So this is constant, mu is constant, u infinity is constant, rho is constant, 4.64 is a constant. So delta is directly proportional to root x. Now we have got this delta. So what will be tau? Tau naught x, we got it as 3 by 2 delta into mu into u infinity. So we got this one, 3 by 2 delta into mu into u infinity. Now substituting this delta value here, we will get 3 mu u infinity by 2 into delta means 4.64 into this will be u infinity goes outside and the remaining under root of here rho also goes upside and x into mu. Now tau naught at x is directly proportional to, so it is inversely proportional to root of x. All these are constants, so x is only the variable. So this is another important relation. Delta is directly proportional to root x. Shear stress at any point in x direction is inversely proportional to root x. So these two you should remember. Now another one, integral 0 to L tau naught x into b into dx. So this is the shear stress, sorry, drag force. So where it is? This one. So this one, this is the drag force. Now if you substitute the values, Fd is equal to, you will be getting, if you substitute this tau x value, that will be 0.646 mu into u infinity into Reynolds number at L into B. What is this Reynolds number at L? This is the plate, this is x direction, x is equal to 0 and x is equal to L. So at this point, what is the Reynolds number? Reynolds number at L is equal to rho u infinity into L by mu. So this is the Reynolds number at L. So that is the drag force. Drag force, we also know that CD by 2 into rho u infinity square into BL. So we also know this. From these two, by equating these two, we can get CD is equal to 1.29 divided by Reynolds number at L. So this is the value of CD. Now there may be different velocity profiles given. For different velocity profiles, we get a different momentum thickness, displacement thickness and boundary layer thickness. Now the velocity profile, if the velocity profile given is u by u infinity is equal to y by delta, the velocity profile is u by u infinity is equal to y by delta. Up to now, I forgot to say, up to now we have found that this delta is equal to 4.64x by Reynolds number x. This delta is for laminar one. If it is laminar, then this delta should be applied. That is for laminar, because we have applied this, where is it? This one. This is for laminar, no? For laminar, mu into du by dy. If it is for turbulent, that will be mu into du by dy plus eta into du by dy. No, where is it? Yeah. So if the velocity profile is u by u infinity is equal to y by delta, then delta is root 12 into x divided by Reynolds number at any position x. Then what is this delta star? Displacement thickness. Displacement thickness is delta by 2. Then momentum thickness is delta by 6. Now if a velocity profile is u by u infinity is equal to 2y by delta minus y square by delta square. If this is the velocity profile, then delta is equal to root 30 into x divided by Reynolds number at x. Delta star is equal to delta by 3. That is the displacement thickness. Then what is momentum thickness? 2 delta by 15. If the velocity profile is u by u infinity is equal to Up to now we have derived the velocity profile, that is 3y by 2 delta minus y cube by 2 delta cube. If this is the velocity profile, what we got here, we got it as 4.64 x divided by Reynolds number at x. Delta star 3 delta by 8. And what is theta? 39 by 280 delta. So how do we get this delta star? Delta star is given by integral 0 to delta 1 minus u by u infinity dy. If you substitute the velocity profile in this u by u infinity, we will be getting delta star similar to this theta. So up to now we have found the values of delta for laminar. The velocity profile is if the flow is laminar, we have found the delta. What if the flow is turbulent? We have seen that for turbulent flow there is logarithmic distribution, or this can also be represented with the flow may be turbulent, the turbulent flow may be logarithmic distribution, or the velocity distribution is the power law. Power law means u is proportional to y power n. Generally this n is equal to 1 by 7. If u is proportional to y power 1 by 7, this is called as turbulent. Now let us see the Blasius equation. If the velocity profile is not given, just use this. Mostly this type of questions will be asked in GATE and ESE. Now for laminar flow, delta is equal to 5x divided by root REX. So this is for laminar. For turbulent, it is 0.371x divided by REX power 1 by 5. So what is REX? At x, the Reynolds number. Then next is CFX, that is 0.664 divided by REX at x, Reynolds number. And this is 0.058 divided by REX power 1 by 5. Next, CD. What is CD? Average drag coefficient. So 1.328 divided by under root of REL. This is for laminar. And for turbulent, it is 0.074 divided by REL power 1 by 5. So remember these values. So this one, this table, and this one. So you no need to remember the derivation, just remember this.